Recording in progress.
Hi students, in the last lecture we have discussed up to energy stored in the capacitor, right? And see, while discussing that, I have given one statement, that is, if capacitor was initially uncharged, then in the process of charging, initially capacitor was uncharged. So in the process of charging, half of the work done by the battery stores in the capacitor in the form of potential energy, and remaining half is lost in the form of heat. This is what we have discussed, right? Let us see. Potential difference equal to V, capacitance equal to C. So we got energy equal to potential energy equal to half CV square. But coming to work done by the battery, that is equal to charge is CV Q into V, that is equal to CV square. So half of the work done by the battery stores in the capacitor in the form of potential energy. The remaining half is lost. This is only when capacitor was initially uncharged. Let us see now if it is initially charged. For example, let us consider a capacitor of capacitance, let us say 2 farad, initially having a charge 2 coulomb, and this is minus 2 coulomb. Now connecting to a battery. Suppose we are connecting positive plate to high potential, negative plate to low potential. So this is one possibility. So whenever capacitor initially charged and when we are connecting to battery, so we have to focus how it is connected. Is it like positive plate to high potential or positive plate to low potential? Okay. So here I have taken connecting positive plate to high potential of the battery. Let us take this is a 6 volt. Now see what happens. So here ultimately what happens is across the capacitor, potential difference must be equal to 6, right? Finally, across the capacitor, potential difference must be equal to 6. If that is the case, charge on the capacitor must be. So we are knowing that Q equal to CV. So C value, it is 2 farad and V value 6. So finally, charge must be equal to 12 coulomb. Okay. So initially having here plus 2, this is minus 2. So finally, what happens is this becomes plus 12 and this becomes minus 12. That means observe carefully how much charge has flown through the battery. That is now 10 coulomb, right? So 10 coulomb charge flows so that this 10 coulomb plus 2 coulomb total becomes 12 coulomb. Okay, right. That means by the battery work done, by the battery work done equal to, so 10 coulomb charge is flowing through the battery from low potential to high potential inside the battery. So by battery work done is, it is a 10 into 6. It is now 60 joule. So this is work done by the battery. Now focus coming to the potential energy. Let us see before connecting to battery, potential energy was initially, I can write it as a q square by 2c, q square by 2c, q value 2, 2 square 4 upon 2 into c value 2, right? Q square by 2c. So this is equal to 1 joule. So initially potential energy was 1 joule. Now see what is the potential energy final value. Again write q square by 2c. Now q value, it is a plus, it is a 12, 12 coulomb, and this is minus 12 coulomb. That means now potential energy q square, 12 square. So 12 into 12, 12 square upon 2c, 2 into 2, 6 times, 6 times. It is 36. So present energy is 36 joule. Initially energy was 1 joule. Now energy is 36 joule. That means what is now increase in the potential energy? So increase in the potential energy equal to 35 joule, right? But see how much work is done by the battery. That is 60 joule. Out of 60 joule, only 30 joule is stored in the capacitor. Remaining is now energy lost. Let us say delta E, energy lost in the form of heat. That is now take in the place of delta E, take delta H, where H stands for heat. So energy lost in the form of heat, delta H, because we use electric field E, right? That's why take delta H. That is equal to, by battery work done is 60 joule, present energy 36, so increase is 35, increase. So remaining is now 60 minus 35, it is 25 joule. So this is now heat lost in the form of, sorry, energy lost in the form of heat. Okay. So you can see here uncharged. Half of the work done by battery is lost in the form of heat. This is now charged. Work done 60. Energy lost in the form of heat 25. So it is not half. That is what we have to keep in mind. Okay. Now see here one more possibility. Connecting positive plate to negative of the battery. Let us see here. So the next possibility. So connecting so we are connecting now negative plate minus 2 coulomb. This is a plus 2 coulomb. Connecting negative plate to high potential of the battery. Okay. Now see what happens. So again, finally, across the capacitor, potential difference must be equal to 6 volt, right? That means finally charge on the plates must be equal to Q equal to C into V, C value 2 and V value 6, total is now 12, right? 12 coulomb. That means on this plate, finally charge will be plus 12 coulomb and here minus 12 coulomb. Okay. Now see carefully. Initially charge was minus 2 coulomb. Now charge is plus 2 coulomb. So how much charge has flown through the battery? That is 14 coulomb. See carefully. From low potential to high potential across the battery, how much charge has flown? That is a 14 coulomb, right? Then net becomes plus 2 coulomb. Then see, work done by the battery is equal to charges of 14 into potential difference 6. So total is now 6 times 60, 6 of 4, 24. It is 84. So 84 joule, right? And see carefully once again. Initially energy was again same, right? No change in that. Q square by 2c. So 1 joule. Finally how much? Again Q square by 2c, 36 joule. So finally 36 joule. That means how much it has gained delta U. It is 35 joule, right? So work done by the battery 84 joule, but gain is 35. So remaining is energy lost in the form of heat. So energy lost equal to work done by battery 84 joule minus gain in the potential energy 35 joule. Okay, see how much it is. 84 minus 35. So it will be equal to, is it a 49? Check once. 40 plus 35. 75. 75 plus 9, 84. It is now 49 joule. Okay. So like this, we can find how much heat is produced in the process of charging the capacitor. Okay. Let us now discuss the next concept. Next one is effect of dielectric on capacitance, right? See what is a dielectric? See, dielectric is nothing but an insulator. It is an insulator. So it is nothing but an insulator, or we can say a substance which has almost no free electrons. Okay. So now we have to focus what is the need of keeping dielectric now between the plates of the capacitor. So we have to focus what is the need of placing dielectric between the plates of the capacitor. See, we are knowing that the purpose of capacitor is to store electric potential energy by storing the charge. But here, while we are charging, see how much charge a capacitor can hold. Suppose having a charge Q here. This is now minus Q. Now between the plates, electric field is now established. As we are keep on increasing the charge, beyond one limit, we can see here between the plates, air is the medium. And we are knowing that air is an insulator, right? But as we are increasing the charge beyond one limit, this air is losing its insulation property. I am repeating, as charge is increased between the plates, electric field is also increased because electric field equal to sigma upon epsilon naught, right? So more is the charge, more is the surface charge density. So more is the electric field. So beyond one limit, what happens is air is losing its insulation property. That means air becomes a conductor. Air becomes a conductor. That means this charge flows through the air. So no longer air is now an insulator. At which electric field this happens? That means the maximum electric field a dielectric can withstand without converting into a conductor is called dielectric strength. I'm writing here dielectric strength. So it is the maximum electric field which a dielectric can withstand without converting into conductor. That is known as dielectric strength. And this value for air, for dry air, it is around 310 power 6 volt per meter. Okay. But if we want to increase the capacity of holding more charge, then we are placing dielectric between the plates. So the main purpose of keeping dielectric between the plates is to increase the capacity of the capacitor. That means it can store more charge and hence a more electric potential energy. That is the purpose of keeping dielectrics between the plates, right? Now focus carefully. So what happens? So when you are placing dielectric between the plates, let us now consider two cases. Case one with battery means still battery is connected to the capacitor. It is with battery. So we are placing a dielectric substance between the plates of the capacitor. It is now filled completely. It is now filled completely. So this is now dielectric. Okay. And you can see here, for example, this left plate is a positive, means plus Q, and this is minus Q. Now what happens is, on this surface, you are having now negative charge on this face. And on this face, it will be positive charge plus. So because of the electric field, let us take it as I have discussed, let us consider there is still battery is there and we are inserting dielectric. See now what happens. Before placing dielectric, field was E naught. Field was E naught. Okay. Now see what happens. So here role of the battery is to maintain constant potential difference. Whether whether dielectric is there or not, irrespective of that, between the plates of the capacitor, potential difference always is equal to V. Okay. That means before inserting capacitor, it was V. Now also it is V only. Okay. So first advantage of filling the space completely between the plates with dielectric is capacitance becomes K times. Let us say C stands for present capacitance, initial value C naught, and K stands for dielectric constant of that substance. K stands for dielectric constant. So first thing, when we are placing dielectric, its capacitance becomes K times. In fact, this we are taking as definition for definition for dielectric constant. Means whether battery is there or battery is not there, irrespective of that, capacitance becomes K times. And this we are taking as definition of dielectric constant. Means this is a fixed. Okay. Next, since there is a battery, it always maintains the same potential difference. Therefore, present potential difference across the capacitor is equal to initial value, that is V naught. Okay. means no change. Next, coming to electric field. Electric field equal to potential difference by separation between the plates, right? It is potential difference by separation between the plates. No change in separation, no change in the potential difference. That means it is again same. No change in potential difference, no change in the electric field. Only capacitance has become K times. Next, you can see charge equal to C into V, right? Now, C becoming K times. So C becoming K times C naught, and V remains same. That means now charge has become K times. Let us take initial value Q naught. Okay, initial value Q naught. That means still there is a battery across the capacitor. Now we are inserting a dielectric. Then what happens is capacity becomes K times. Charge also becomes K times. Okay. And see carefully how much extra charge has flown through the battery. Initially charge was Q naught. Now charge is K times Q naught. That means extra charge that has flown. Let us take it as delta Q, extra charge that has flown. Final value minus initial value. So K Q naught minus Q naught. So Q naught into K minus 1. So this extra charge has flown across the battery. We can say from low potential to high potential across the battery, right? Next, let us calculate potential energy. Potential energy means I can write here half CV square, half CV square. Now, V value remains the same, but C value, it has become K times. That means potential energy becomes now K times. Okay. So starting point is definition of dielectric constant. So how it is defined means capacitance after inserting dielectric upon capacitance before inserting dielectric. That means capacitance becomes K times. That is our definition part. From there, we are getting now remaining all these things, all quantities, having more charge, more potential difference, same potential difference, same field. Okay, right. Now let us see. Now without battery. Let us take now second case without battery. That means initially capacitor was charged. Now battery is removed. Then inserting the dielectric. So now there is no battery. Capacitor is charged, and after that battery is removed. Now insert dielectric. Okay. So when you insert dielectric now, inserting dielectric after removing the battery. Let us initial charge Q naught. This is minus Q naught, right? Now see what happens. Again, first condition. Capacitance becomes K times. No change in that because that is the definition of dielectric constant. So first one, C equal to K times C naught. Okay. Next. Next, see what we can say. Since there is no battery, there is no change in the charge. Charge remains the same. Therefore, Q equal to Q naught. And we are knowing that Q equal to C into V, right? Q, there is no change in charge, but capacitance has become K times. So that implies Potential difference becomes now 1 by k times. What is it? Potential difference becomes 1 by k times because charge equal to C into V. No change in charge. C becoming k times, then V should become 1 by k times. Since V becomes 1 by k times, electric field also becomes 1 by k times. Electric field also becomes 1 by k times. Right? Next, coming to energy, right? So coming to energy, see what we can say. So here we can say, since the charge is a constant, I am taking energy equal to Q square by 2C. There is no change in the charge, but coming to capacitance, it has become K times. That means potential energy becoming now 1 by K times, right? This is what we can conclude regarding charge, potential, field, and potential energy. So case 1, with the battery present, no change in potential difference, no change in the electric field. Charge becomes K times. But coming to here, charge remains the same, right? Next, field becomes 1 by K times. Potential becomes 1 by K times. And see carefully here one more result, what we can say. One more we can derive here. Relation between induced charge now let us derive relation. So here charge is Q naught and see how much charge has induced on the dielectric substance. We are seeing some charge is now induced here. It is a minus and this is a plus. Okay. Suppose charge is Q naught here. Now what I can say here, see carefully. Electric field between the plates is becoming 1 by K times. And if you observe carefully, because of Q naught, field is right side, that is E naught. Because of the induced charge, field is left side. Field is left side. Take it as E dash. And what I can write here, E naught minus E dash is equal to net equal to E naught by K. See carefully. E naught. It is a field due to the charge Q naught because of the charge on the plates. E dash because of the charges induced inside the dielectric plus 2 minus left side. I have taken that as E dash. Net is equal to E naught by K, right? That means from this E dash is equal to E naught into 1 minus 1 by Q, right? And we are knowing that field equal to sigma upon epsilon naught, or I can say in the place of sigma q by a epsilon naught. Okay. Now see here what I can write. A and epsilon naught remaining is now q, right? So here I can write here q in the place of q. I am taking q dash. Charge induced in the dielectric, that is equal to, in the place of E naught, it is a Q naught into 1 minus 1 by Q. So how much charge is induced on the face of the dielectric? It is given by Q naught into 1 minus 1 by Q. And see here I have taken only magnitude. Remember, if this is a positive, induced one is negative. If it is negative, induced one is positive. That means if I am taking Q naught positive, this will be negative. So I should write here negative sign. So why negative sign means? Because sign is opposite. If it is a plus, minus. If it is a minus, it is a plus. So Q dash equal to minus a Q naught into 1 minus 1 by K. And we are knowing for conductors, or you can say for metals. For metals, K value, it is infinity, right? So K value infinity means 1 by infinity, that is 0. So Q dash equal to minus a Q naught. And I can say directly from here, K value infinity means E naught by K, that becomes 0. That means the field becomes 0 between the plates if we are placing a conductor. Okay. So this relation we use frequently while solving problems. Induced charge how much? Q dash equal to minus a Q naught into 1 minus 1 by K. If it is a conductor, then how much means? If it is a plus a Q naught, it will induce minus a Q naught because this is a 0 for conductor, right? So Q dash equal to minus a Q naught, right?